Welcome to the video over Chapter 5. This will be the first of two parts. We'll break up the math into two different videos. So what are we going to do in Chapter 5? We're going to cover gases and how they work and how we can use a variety of different things to calculate how they work. So one of the things that we're going to really focus on in Chapter 5 is pressure. Right, and the pressure of a gas. The pressure of a gas is force per any unit of area. There's many different ways to describe pressure. So if you've ever flown or if you've ever increased your elevation, you will have seen the difference in pressure in your ears when they pop. One of the things that we're going to do is we're going to have to convert units from one to another of pressure. The most common unit of pressure is millimeters mercury. 1 millimeter mercury is equal to 1 torr. So our book usually uses millimeters mercury. The book that I had when I was a Gen Chem student and that I bring in practice problems from use torr. We just have to remember that 1 torr is equal to 1 millimeter mercury. You will not have to memorize any of the conversion factors to go from, let's say, pascals into torr or atmospheres into torr, because I will give that to you. But you do have to know that millimeters mercury is equal to 1 torr. So, that's going to be the most common way we measure pressure, is millimeters mercury. However, the most commonly used pressure unit is atmospheres. And so atmospheres, 1 atmosphere is the average air pressure at sea level. As you can see here, that's where we get atmospheres. Another conversion factor that we're going to have to learn is that 1 atmosphere is equal to 760 millimeters mercury or torr. And the only reason we're going to have to know this one, you'll be given it on an exam, but you'll be using it enough to where you'll memorize it. The reason why we have to do this is because pressure equals atmospheres for all of the gas laws that we're going to talk about. So we will have to remember how to convert units. We are going to do a lot of conversion of units from one to another in this chapter. And so let's say, as an example, you are looking at a gas with 785 torr, and you wanted to know what it was in atmospheres. So to do that conversion, you would divide by 760. And when you do that, you get 1.03 atmospheres. Right? So when we go from millimeters mercury to atmospheres, we're going from something bigger to longer, or bigger to smaller. We're going to divide by the conversion factor. Whenever we go from atmospheres to millimeters mercury, we're going from something smaller to larger, we would multiply by the conversion factor. And so, to practice this, I want you guys to do number 26 and number 27, and that will be due on those. I want you guys to turn in on Monday the 24th. Right, so that we can just refamiliarize ourselves with how to convert units. So in class we are going to cover the simple gas laws, the basic gas laws. We're going to, however, look at the interaction and this one using the ideal gas law of the 4 basic properties of a gas. And those are pressure, volume, temperature, and the number of moles, or the amount. These are the 4 basic properties of a gas. And we'll look at the relationship between 2 of these properties in class, and we'll look at the overall relationship between everything in just a second. Pressure has to be in atmospheres. Volume has to be in liters. Temperature has to be in Kelvin. Remember, to go from degrees Celsius to Kelvin, you add 273. And then N is the number of moles. Right, so these are the 4 basic properties of gas. When we look at the interaction of all of these properties, we can find what's known as the ideal gas law. And many of you guys are probably familiar with this. PV equals NRT, where P stands for pressure, V stands for volume, N stands for moles, and T stands for temperature. R stands for the gas constant. And so the gas constant you will be given, but again, you'll use it so much that you'll memorize it, is 0.08206 liters, atmospheres, Kelvin, moles. So if you ever had a question, if you were given a problem with like this on an exam, and you knew, okay, I need to use PV equals NRT, but I can't remember what the V, the P, or the T have to be in, what you can do is you can look at here as your constant, and it will tell you exactly what you need. You need liters, atmospheres, and Kelvin. Use constants. Whenever we're giving you a constant, there's a reason why we give it to you. Use the units to help drive your conversions. So how can we use the ideal gas law? And one of the things that I want you guys to do is look at PV equals NRT. I will not do it, we'll do it slightly, but I want you guys to try to solve for P, solve for V, solve for N, and solve for T, right? So manipulate this equation algebraically so that you can get used to solving for these different things, because we'll be using it to solve for those different things. So let's look at an example problem. This will be number 37 at the end of the chapter. So we want to know the volume of a helium gas, and we're given some measurements. We know that it has 0.118 moles. We know that it's at 0.97 atmospheres, and we know the temperature is 305 Kelvin. Right? And so again, so we want to use PV equals NRT. So what I would recommend doing is, before you do any math, before you start anything, is go ahead and solve for what you want to solve for. So we want to solve for volume. So we'll divide by pressures. And so what we get is volume is equal to nRT over P. Now we can start plugging in what we know. So we know the number of moles. We know the gas constant. We know the temperature. And that's going to be divided by the pressure. And when we solve for this, we get 3.0 liters. Now there's a second part on that question, which saying the volume of helium gas with this is this. Would the same thing happen if the gas was argon? And so I want you guys to think about that answer and maybe even calculate it out. So let's look at another ideal gas law problem. This is going to be number 45. So, we have dry ice. If you've ever seen dry ice, you know it sublimates, or it goes from a solid directly to a gas. So we put some dry ice in a balloon, and we have 28.8 grams. Alright, so we have 28.8 grams of dry ice. And the balloon we put it in has a we know the volume of balloon. That's what we want to find. So we want to find the volume. But we know when all of the dry ice sublimates or turns into gas, the pressure is 742 millimeters mercury. And the temperature is at 22 degrees Celsius. So, the first thing we need to do in these equations is to make sure that our units are where we want them. So, the first thing I would recommend doing is looking at this guy here, right? N stands for moles. We don't have anything with moles, but we were given an amount. So we have 28.8 grams of CO2, and we know the molecular weight of CO2 is 44.01 grams per 1 mole. So when we do this calculation, we get 0.654 moles of CO2. So now we have moles. So that's the first step. The first step is if you're given grams for a PV equals nRT equation, you need to find moles, just like it has been before. The second step is to then do all the conversion of our units. So we have 22 degrees Celsius, and we need that in Kelvin. So we said to turn degrees Celsius into Kelvin, you add 273. So this is going to be 295 Kelvin. And then we're going to have to turn our 742 millimeters mercury into atmospheres. And to do that, we divide by the conversion factor, which is 760 millimeters mercury per 1 atmosphere. And when we do that, we're going to get 0.976 atmospheres. So when we finish with this, we are now ready to solve the problem. But we cannot solve the problem until we do all these conversions first. So if you know you're doing PV equals nRT, you have to have moles, Kelvin, atmospheres, or liters to solve for this problem. So I'm going to rewrite what we found. So we found moles as being 0.654. This was number 45. Moles of CO2. We know the temperature, 295 Kelvin, and we found the pressure was 0.976 atmospheres. And so we know PV equals nRT, and we're solving for volume. So again, if you want to plug in the numbers and solve it with the numbers in it, go ahead. But if you want to solve it like this, you can also do that as well. So we know the volume is equal to 0.654 times the gas constant times the Kelvin divided by the pressure. And when we do all of this, we find that the volume of the balloon is 16.2 liters. And that would be our final answer. So, this is using PV equals nRT, using the ideal gas law, right? It's the same tracks, it's the same way to solve it, it's just a slightly different starting spot. And so for practice of this, I want you guys to do number 47 and number 51. And I want you guys to do that for Monday, September the 24th. At the same time as your conversions. So, we can use the ideal gas law, and I'll show you how we get to this spot in class. We can use the ideal gas law to calculate the density of a gas. So the density is equal to the pressure of the gas times the molecular weight of the gas divided by R times the temperature. So we can not only find the density of a gas, we can also find the molecular weight of a gas. And so number 57 in your book asks you to find the molecular weight of a gas. And so you have the gas. So we know that the volume is 248 mils. And we know we got that 248 mils because we had 0.433 grams. The pressure is 745 millimeters mercury of this gas, and the temperature of the gas is 28 degrees Celsius. And so we want to know how much does this gas weigh. So the first step is to find all the variables that we can. So let's start with pressure. So it's in millimeters mercury. So we know we have to divide by the conversion factor. So see what I mean by, you guys will be using this conversion enough to where you'll just pretty much memorize it, because pretty much every pressure that you're given in these problems will be in millimeters mercury or some sort of other pressure so you have to convert it. So that's the first thing we'll find is the pressure. We'll find the second easier thing, which is temperature, which is 28 degrees Celsius plus 273, and that's going to equal 301 Kelvin. Right? And then the other one that we can find is density. So we have to remember what density is. Density is grams per liter. And so we're given grams, but we're given milliliters. So we have to convert 248 milliliters into liters. So we're going to divide by 1,000. And so we're going to have 0.248 liters. And so to find the density, all we do is to take the number of grams divided by the number of liters. And that will give us 1.75 grams per liter. So we now have pressure, we now have temperature, and we now have density. So now we are ready to solve this problem. So we know density is equal to pressure times the molecular weight divided by RT. So let's go ahead and solve this equation for what we're trying to look for, and that's the molecular weight. So we're going to start by multiplying by the R and the T. So we get RT times density is equal to pressure, molecular weight, divide by P. So that's going to equal molecular weight, RTD over P. So now we can just plug in everything that we found. So we know that R is not going to change because it's a constant. Temperature was 301 Kelvin. The density we found is 1.75 grams per liter. We're going to divide that by our pressure, which is 0.98026. So the molecular weight of this gas, after we do all of that math, is 44.10 grams per mole, right? Because we're looking at molecular weight. So we can use the ideal gas law will be the thing that we will constantly use in this chapter. And that the reason is because it helps us solve so many problems. And so to practice this, I want you guys to do number 59 and number 55 at the end of the chapter. And these will be due on Wednesday, September 26th. And so this will end the first portion of the math that we have to do, where we look at just the ideal gas law and we look at it to calculate molecular weight. In class, I will teach you about simple gas laws. And so when we're just trying to calculate 2 of the 4 different properties of a gas. And so there will be shortly a video over the second part of Chapter 5.
And he said to the man, run in the sand.